Anoop Singh with us from HRI. He will speak on the moduli space of logarithmic connections over a compact Riemann surface. Well, please go.
Thank you so much. First of all, I would like to thank organizers, such a wonderful this virtual math fest, and giving me this opportunity to speak here. So, title of my talk is. Wait a minute. Someone is okay. Sorry, sorry. So title of my this talk is on the moduli space of logarithmic connections over a compact Riemann surface. So. So as far as history and motivation is concerned, so the notion of moduli spaces are very fundamental in classification problems in algebraic geometry. That is, if we are given a collection of objects and equivalence relation, then the problem is to describe the set of equivalence classes. And here comes the notion of moduli spaces. In 1993, Nitsure constructed the moduli space of semi-stable logarithmic connections. And again, in the same year, kind of, but later year in 1994, Simpson gave a very general recipe to construct the moduli space of lambda modules, where lambda is a sheaf of differential operators. So once we have a moduli space, we study its a lot of algebra geometric invariants. So Picard group is one of them. And it has been studied extensively by many algebraic geometers. So in 2005, Biswas and Raghavendra studied the moduli space of logarithmic connections, singular exactly over one point with fixed residue, and described the algebrogeometric invariants of this moduli space, like algebraic functions and Picard group, and also compactification. So here we study the same for the moduli space logarithmic connection, singular over a finite subset of a compact Riemann surface with fixed residues and of course without fixed residues. So here we are replacing our moduli space rather than singular exactly at one point to finitely many points. So next thing, definition and all. So throughout this talk, X will denote a compact Riemann surface of genus greater than or equal to 2. And S is a finite subset of X such that these points are disjoint. They are not same. So let Z is equal to X1 plus dot 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 plus Xm denote the reduced effective divisor associated with this subset S. The notion of logarithmic connection was introduced by Pierre Dulin in 1970 in this lecture note, which is very useful note, and it studies the regular singular points of differential equations. So as far as definition is concerned, let E be a holomorphic vector bundle on X. A logarithmic connection on E singular over S is a C linear map D from E to E tensor omega 1x tensor OXZ. This is a line bundle corresponding to divisor Z, which satisfies this Leibniz identity, which is D of Fs is equal to FDS plus DF tensor S, where F is a local section of OX and S is a local section of E. So can you hear me properly? Hello? Hello?
Yes.
Hello? Okay. That's great. So when logarithmic connection is given, we can talk about residue of a logarithmic connection. So by a pair in this talk, we mean that D is a logarithmic connection in E singular over X. So the subset S, we take any point X beta in S. The fiber is canonically identified with this complex number by sending a meromorphic form to its residue. Actually, because of this, given a pair, we get an endomorphism in this fiber of a vector bundle, and this endomorphism is called the residue of a logarithmic connection at this point Ex beta, where Ex beta denotes the fiber of E at X beta. Now given such a pair ED, due to Otsuki in 1982, we have a this formula which relays the degree and the trace of the residue, and this gives the constraint on the degree. Means you can fixing this residues, you can immediately get what is degree is. So degree of E, sorry, degree of E plus summation j is equal to n to m trace residue d comma xj is equal to 0, where the this notation res d comma xj, this is the residue of this logarithmic connection. Now this formula is very important, we will see. Coming back to the moduli spaces of logarithmic connection, the slope of a vector bundle is defined by degree upon rank, and a pair ED is said to be semi-stable. So this is, I'm talking about the semi-stability of logarithmic connection. So a pair ED is said to be semi-stable, respectively stable, if for every non-zero proper subbundle f of E, which is invariant under D, that is df, the sections over of f goes inside f tensor omega 1x tensor ox. Oh, I forgot to write here z. Okay, that's fine. We have mu f less than or equal to mu e. The slope is less than or equal to mu e for these bundles which are invariant under D. Respectively, mu f is strictly less than mu f, where mu e is a slope of E for the stable one. As we know, for stable vector bundles it is true for every non-zero proper subbundle, but for logarithmic connection it has to satisfy only those proper subbundles which are invariant under D. Now we consider holomorphic vector bundles of rank n and degree D uh, such that D and n are co-prime. For I is equal to n to m, we fix rational numbers such that multiplication with n lambda I belongs to Z. Now we consider the pairs ED satisfying the following conditions. ED is a logarithmic connection of rank n and degree D, singular over S, with fixed residues. So here I'm fixing residue of this special kind. I have chosen the numbers in Q and such that n into lambda I in Z. So residue I'm choosing lambda I into identity of these identity morphism on the fibers of a vector bundle E. So this is for all I is equal to 1 to m. So from the above assumptions and from uh, this Otsuki's formula, we have this. We immediately conclude that d plus n summation I is equal to m lambda I is equal to 0. And if we assume further, because d and n are co-prime, we will see that this logarithmic connection, because of this relation, this is automatically stable. So I'm saying this logarithmic connection is stable. It doesn't mean that vector bundle is stable. Vector bundle may be unstable or semi-stable, whatever, but this is automatically stable. Now let MLCND denote the moduli space which parameterizes the isomorphic class of pair CD. Then MLCND is known to be irreducible smooth quasi-projective variety over C. This is due to Nitsure and Simpson, and this irreducibility follows because we have considered, there is a theorem by Simpson. We have considered. I'm sorry. Uh, I'm sorry. It's going. It's jumping here. Uh, because we have considered the genus of curve is greater than or equal to 2. Okay. So, so here is the first result. So first of all, let MLC prime ND subset of MLC ND denote the moduli space of logarithmic connections whose underlying vector bundle is stable. See, the vector bundle is stable, but the vector bundle need not be stable, underlying vector bundle. So I'm taking further small subset of this where underlying vector bundle is stable. Now let UND denote the moduli space of stable vector bundles of rank n and degree d over x with n and d co-prime. It is known that UND is a irreducible smooth projective variety. It's not quasi-projective variety, it's projective variety. But MLCND is a quasi-projective variety, and it is open subset of this. So MLCM prime ND is also quasi-projective variety. So we have a compactification of MLC prime ND. See, still I'm able to compactify due to this UND, but not MLCND. This is again an open problem to compactify because this is a quasi-projective variety. So what is the natural compactification is MLCND? It is not done. So it is an open problem. So MLC prime ND, I'm going to compactify this thing. So theorem is there exists an algebraic vector bundle E over UND. this is xi, capital Xi, such that MLC prime is embedded in this projectivization of this vector bundle with complement as the hyperplane at infinity. So because of this is a smooth compactification of this MLC prime ND, and this theorem is used in proving this Picard group isomorphism. So before going to this, so we have a natural morphism P from MLC prime ND to UND, because we have considered MLC prime ND is all those pairs E comma D where underlying vector bundle E becomes stable. So if E is stable, then we can send just forgetful functor sending this pair ED to E. Then it will give you a UND. It goes into this moduli space. Now there is a criterion for the existence of a logarithmic connection in a vector bundle over a compact Riemann surface with prescribed residue. It has been proved due to Biswas, Dan, and Paul in 2018. And because of this, and because our residue satisfies this formula that d plus n summation lambda is equal to 0. Because of this, it is surjective. So there exists a vector bundle, and if residue satisfies that relation, d plus n lambda I is equal to 0, summation n summation lambda is equal to 0, then there exists a vector bundle, holomorphic vector bundle over X with logarithmic connection in this vector bundle, having those residues lambda into identity of these. So because of this result, this criterion P is surjective. Now this morphism will induce a homomorphism on the Picard group, which sends a line bundle here, taking pullback here of Picard groups, where this Xi sends P pullback of Xi, where Xi is algebraic line bundle over this. This homomorphism of Picard group is an isomorphism. So we have that Picard group of these two moduli spaces are actually isomorphic. And proving this theorem, this is a core result. This has been used. The compactification has been used. Okay, going one slide down. So again, similar result can be proved. Fix a holomorphic line bundle L over X of degree D and fix a logarithmic connection. Now DL, actually now what we are doing is we are considering moduli spaces kind of with fixed determinant, but here we cannot fix just line bundle, we have to fix some connection on it because we are parameterizing the pairs E comma D. So that's why fix a holomorphic line bundle L over X of degree D and fix a logarithmic connection DL singular over X with residue this. Now this is being a complex number because endomorphic, because fiber of this L is isomorphic to a complex number. So lambda J is already chosen to be a rational number. So n into lambda J. So let MLC NL contained in MLC ND be the moduli space of parameterizing isomorphic classes of pairs such that the top form of E comma D tilde is isomorphic to this pair L comma DL. This isomorphism is means there exists an isomorphism from top pair to L which satisfies the commutative diagram where D tilde and DL are connections going from top exterior form to top interior E tensor with omega 1x tensor OXZ, and similarly here. And D tilde is the logarithmic connection on this induced by D. We go further down. We consider this moduli space. Now we consider again the moduli space whose underlying vector bundle is stable. Why? So that we can get a morphism from this MLC prime NL to ULND. What is ULND? ULND is the moduli space of a stable bundle, stable vector bundles with fixed determinant. Now, because of this variety, we have a natural morphism of variety that induces a homomorphism of Picard groups, and here also these this Picard groups are isomorphic. This homomorphism of Picard group is an isomorphism. Now, actually, now this is the main theorem of this talk. So assume that genus of X is greater than or equal to 3, then this MLC prime NL, this is the moduli space of logarithmic connection kind of with fixed determinant L whose underlying vector bundle is stable. Then the global sections are actually constant, means algebraic functions are constant maps on this moduli space. Algebraic functions, I mean regular functions. Yeah. So to prove the above theorem, we proceed as follows. Actually, theta, we take the ample generator of this group, and C theta sheaf of sections of open subset are holomorphic connections in this. And for every open subset, the space of holomorphic connection in affine space modeled over this. Therefore, C theta is omega 1 ULND torsor. So we take a torsor, and the two torsors C theta and LC prime ND, these two torsors are actually isomorphic as an algebraic variety. So to prove that this constant algebraic functions over MLC prime ND, it is enough to prove from C theta, this space. So it has been proved using Atiyah bundle, and means computing the global sections of symmetric powers of Atiyah bundle and Hitchin fibration on this T star of ULND. Using these two techniques, we are able to prove, and in this way, this will complete this theorem. Now, with arbitrary residues also, we can characterize algebraic functions. So we fix a pair L comma DL as above, but without fixing residues. I'm not fixing here residues at all. NLC NL denote the moduli space parameterizing all pair CD satisfying this condition. N and D are mutually co-prime, as you know. The residues lies in the center of this Lie algebra associated to GLNC. This is so residue can be anything. I'm not fixing residue, but I'm fixing this condition that trace should go in integer due to certain reasons. And it is a logarithmic connection singular over S of rank n and degree D, which satisfies this condition as we saw previously. Then this moduli space irreducible normal quasi-projective variety. It need not be smooth. This moduli space need not be smooth. So this is a irreducible normal quasi-projective variety over C. So here is somehow this algebraic function. So V is equal to, we take this tuple such that n into alpha j belongs to Z, and this will satisfy this condition. So this is the subset of CM. So we can define a map from NLCNL to V, which sends this pair to trace divided by the ranks. So from the Otsuki's condition, actually these numbers will go inside V because they satisfy this condition. Then size and surjective homomorphism. Size actually surjective homomorphism, and and we have this theorem. So let X be a compact Riemann surface of genus greater than or equal to 3. Then every algebraic function on NLC and L factors through this map. So if I take any algebraic function on this, then there exists a unique function from V to C such that this diagram commutes. So this result means this. And here are the references for this. This is the thing where I study. This is the paper. This is in an archive also. Moduli space of logarithmic connections singular over a finite subset of a compact Riemann surface. This to appear in math research letters. And this is the paper from where I got motivation, Biswas and Raghavendra. And this is the paper where criteria for logarithmic connections. And this is a Nitsuris paper, of course. And these are the papers of Simpson's where he talk about moduli spaces of lambda modules. And this is the Otsuki's paper, residue formula for Chern classes logarithmic connection. Now, thank you so much for this. Hello.
Thank you so much.